Hi, my name is Jim Freericks. I'm a professor of physics at Georgetown University, and in this talk I'm going to tell you how we can bring the physics back into the junior-senior quantum mechanics course. Let's face it, we are physicists, we're not mathematicians. Let's teach physics in our quantum mechanics classes. We're on the verge of a second quantum revolution. Let's bring that excitement into the quantum mechanics classroom. Here's the problem. Most courses and textbooks use the coordinate representation for wave functions in the differential equation form of the Schrödinger equation. And you might think, yeah, of course, that's the only way that you can do it. Is this really needed, though? The answer, it might surprise you, is no. And in this talk, I'm going to show you how you can teach quantum mechanics in a more representation-independent fashion. We're going to use strategies from physics education research. Look, we all know quantum mechanics is non-intuitive and subject to common misconceptions. And physics education research tells us let's teach the conceptual ideas first and bring the formalism in later, because once the conceptual ideas are firm, students are able to understand, grasp, and work with the more theoretical ideas in a much easier fashion. We're going to then integrate the theoretical ideas with experimental ideas, and we're going to relate the theory in the class to real-world experiences of quantum mechanics. The class is divided into 4 quarters, and I'm going to tell you about each of the different quarters. In the first quarter, we focus on the concepts of superposition and entanglement. These are the conceptual ideas of quantum mechanics that students have so much trouble understanding. We're also going to introduce the formal ideas of Dirac notation and of Pauli spin matrices. To introduce the conceptual ideas, we follow the groundbreaking work of Feynman in his QED textbook, of Daniel Styer in The Strange World of Quantum Mechanics, and of Ed Taylor, who developed animations that animated the drawings in the Feynman QED book to help visualize and bring to life the conceptual ideas that were being taught in the Feynman text. The topics that we cover, we start from a spins first perspective, but we actually take a lot of time to focus on the classical mechanics of magnetic needles and current loops, because frankly, this is a really hard question. How do you understand the forces that a magnetic field applies to a current loop and understanding the motion of precession? But once we have that in place, we can then talk about the Stern-Gerlach experiment. We do Wheeler's delayed choice variety of the Stern-Gerlach experiment. We talk about Einstein-Podolsky-Rosen experiments. We talk about Bell experiments. And we also talk about nuclear magnetic resonance. Then we introduce light in the way that Feynman does. With this, we can talk about partial reflection of light, single slit diffraction. And I want to encourage people to recall that single slit diffraction does have wave behavior to it. We often teach quantum mechanics and say in the single slit it's a particle, but it really isn't. It's still a wave even in single slits. Two slit diffraction, mirrors, lenses, quantum seeing in the dark or interaction-free measurements, which is a remarkable experiment that every student in quantum mechanics should know, Hanbury, Brown, and Twist, and the Hong-U-Mandel experiment. And then with the formal side, we talk about Dirac notation, spin operators, and Pauli matrices, which allows us to talk about quantum key distribution and Rabi oscillations. Now, in the second quarter of the course, we do have to do some formal development. The formal development is primarily in developing the 4 operator identities that allow you to do everything in quantum mechanics. This is the Leibniz rule, which is the product rule for the commutator. The Hadamard lemma, which says that when you have a similarity transformation of an operator by an exponential, e to the a, b, e to the minus a, then you can rewrite that as an infinite series of an infinitely nested commutators of a with b. The exponential disentangling identity, this is an identity that comes from Lie group theory and Lie algebra, and it's one that most people, except those in quantum optics, do not know, but it allows you to factorize exponentials of operators when the operators in the exponential satisfy certain Lie algebraic properties. And then the last one is the Baker-Campbell-Hausdorff formula, which takes a product of exponentials and rewrites it as the exponential of a sum of terms. So in this section, we really don't develop any new experiments. We primarily develop the identities, but we do talk about and solve for position and momentum eigenstates. And we give a more formal description of the Stern-Gerlach and two-slit experiments, including the delayed choice variants, now doing it in a fully quantum mechanical and fully formal fashion. In the third quarter of the course, we developed the factorization method. This is a method developed by Schrodinger to solve the Schrodinger equation without using any differential operators. It was developed about 15 years after he introduced the Schrodinger equation, but it's not known to many people. It generalizes the abstract algebraic way that we solve the harmonic oscillator to being able to solve all problems this way. And then we discuss a number of different example problems that we solve. We start with a simple harmonic oscillator, including both coherent and squeeze states. This allows us to talk about Einstein-Podolsky-Rosen experiment and introduce the time of flight experiment. Now, I want to encourage you to teach time of flight in your classes rather than doing something like saying, I have a particle in a box and I'm measuring its position and it collapses to a delta function, and then I let it evolve and I measure its position again and so forth. No one does experiments measuring position that accurately in particle in a box potentials, but people do time of flight, and time of flight is far more marvelous and interesting to introduce into a quantum mechanics class because you start a timer when a certain event occurs, and then you time when the particle hits your detector. By taking the distance between the source and dividing it by the time, you actually get the momentum of the particle, but you also get the location of the particle because it hit your detector. And so you have both the position and momentum of the particle at the same time. Does that violate quantum mechanics? It actually doesn't, and it allows you to have a wonderful discussion about how the time of flight experiment works. We also talk about angular momentum. We bring in the Morse potential and talk about molecular rotational spectra. And then we do hydrogen, and hydrogen is where we really focus on a lot of different experiments. In addition to just the spectral lines of hydrogen, which are wonderful to talk about, and nearly everyone does, we talk about the Pickering-Fowler lines and how that actually convinced people that the Bohr model was correct. We talk about how measuring spectra accurately enough can allow you to actually weigh the atom and how that led to the discovery of the deuteron. We talk about how even more accurate measurements of the spectra allow you to actually determine the size of the proton in the atom. And we also talk about E2E spectroscopy, which allows you to directly image the wave function of the hydrogen atom in momentum space, as opposed to what we often tell people, which is if I were to measure the electron in the hydrogen atom, the mod psi squared dx is going to give me the probability distribution for the electron to be found there. But we never measure the electron that accurately in position space. We don't know how. We, however, do it in momentum space, so it's a wonderful thing to teach the students. And then we talk about perturbation theory, which allows us to talk about hyperfine transitions, radio astronomy, and precision measurements, including atomic clocks. In the fourth quarter of the course, we do time evolution and second quantization, and you did not hear me incorrectly, second quantization. We do, with time evolution, which we introduce via the Trotter formula, we then talk about nuclear magnetic resonance spectroscopy and magnetic resonance imaging. As I mentioned, we do it all via the Trotter product formula as opposed to introducing the differential equation way of doing it, which frankly is really confusing and hard to follow. Trotter formula is a much better way, in my opinion, to do it. We then quantize light. And with that, we talk about heterodyne and homodyne detection because the frequency of light is so fast, you can't directly measure it. We talk about how you make single photon sources and why a single photon source is different from just dim light. We talk about how you detect single photons. And finally, we talk about how LIGO works, which is one of the crowning achievements of this decade and something that should be in every quantum mechanics course. So I do not teach the Frobenius method. I do not teach delta functions. I do not work with second-order differential equations and wave functions. I've created a word cloud that shows all the different experiments that I do cover in this one semester-long class. Let's bring the physics back into the quantum mechanics classroom. Let's teach students about the second revolution in quantum mechanics, particularly with a focus on quantum sensing, which is what you get out of a class that's taught in this fashion. The course is coming to edX in the fall of 2021. It'll be released in middle of August. I encourage you to take it if you'd like to learn more about how this works, or you can just contact me by email. And I would like to thank the people who've helped me in this project. Dylan Cutler and Lucas Vieira Barbosa are two undergraduates who worked on developing the JavaScript animations. Pia Betia and Daphne Maniatis are two undergraduates who helped me with putting the course on edX and also helped with giving me a student's perspective with the materials as I was developing them. And Anna Cruz is a member of our Center for New Designs in Learning and Scholarship. That's a unit of Georgetown University that helps with innovations in teaching. And of course, the National Science Foundation also helped fund this work. Thank you very much. And Feel free to send me an email at james.freericks@georgetown.edu if you have any further questions.